Welcome to Aerodynamics. In this lecture, we will continue our introduction of the fluid mechanics principles that we are going to need in aerodynamics. In a previous lecture, we talked about the sources, the basic fundamental fluid mechanics sources of the aerodynamic force generation, and we said these were due to friction, viscous friction, as well as pressure on the surface of any flying object. So where we're heading next is to the boundary layer theory. And if you take any object moving in a fluid, then you will, so for example, this wing section, where it's moving in a fluid at a velocity of u infinity, and the fluid has density and a viscosity, then what you will notice that there is going to be an imaginary layer. It's not something that you can see, primarily because the fluids we deal with are transparent, air and water, but you can see implications of that in terms of you can measure this boundary layer, and it's a region where viscosity is concentrated. We'll come back to this later on, so don't worry about it. But the primary reason why you have a boundary layer is the no-slip condition. So right on the surface of the object that is going through a fluid that is a gas or a liquid, the fluid element that's in touch with the object will have the same velocity as the impermeable solid object. And as we see from this cartoon, far away from the object, we expect that the air or water would be passing by this, going past this wing at the undisturbed velocity of u infinity. So we have a region where our velocity would go from the no-slip zero velocity all the way to u infinity, and we get a velocity distribution, typically not a jump type velocity distribution, but rather a continuous increase in velocity, albeit in a very, very thin region. We're talking on the order of millimeters to centimeters for very large aircrafts. So we have a boundary layer, and once we start talking about the no-slip condition and talking about the velocity differential between the surface of the wing and the free stream, then we need to talk about the shear stress, because the shear stress comes from the straining of the fluid, so the strain rate of the fluid. So you see the fluid is moving sort of in this picture, it's moving at different velocities at different locations, and that essentially creates that relative motion creates a transfer of force due to viscosity, which we call shear stress. So one implication of the boundary layer is that, or at least one factor that is important when we're considering boundary layers is the shear stress. So it's something that's going to keep coming up all along. And the other force that we've also noticed in the previous lecture is that there is a pressure distribution around a wing or around an aircraft or around a body moving in a fluid, and that pressure creates a force. Now we have those two fundamental forces that are being felt by the boundary layer, and they're part and parcel of the boundary layer: the shear stress and the pressure. And the interaction between them is actually going to be very interesting. So let's see. Let's look at this airfoil, and it sees the air. So that's our airfoil. it sees the air coming in undisturbed at a velocity u infinity, so far away from the object. Far away from the object, we have the flow coming at u infinity. And now let's take, so if I go even, so that's ahead of, we're talking upstream of the object, but if I go laterally to the object, I also have the flow going past at u infinity. And if I'm sufficiently far away from my airfoil, then the flow will, that air particle is going to go past undisturbed. Essentially, it's the airfoil that goes past it, but now we're past the point of talking about relative velocities. We've covered that enough. Go to a previous lecture to look at that. So the flow is undisturbed, and that's the flow path. And a flow path also signifies a streamline. And from our fluid mechanics study, a streamline can be treated from a mass flow perspective to be a solid object. So here's now the story that we're going to build. This is a solid object, and there's a streamline here that behaves like a solid object because the definition of a streamline is that there's no flow that crosses it. Indeed, we have a fluid element that is close to the object, so will follow a path like so, like I'm tracing with the laser pointer. So it's going to curve in a shape that approximates the shape of the airfoil with to a first degree. There are complications to that and other details that can happen. So you'll see we'll feel the disturbance. The streamlines will feel the disturbance. But if we're sufficiently far away, that streamline will be a straight line and will not feel the effect, for all practical purposes, will not feel the presence of the airfoil. Great. So now, if you look at the distance between, so now there is flow going between this solid object for all mass flow purposes. This is the mass flow rate that goes through this section, will continue going through other sections, that is between the airfoil and the top streamline. So let's see how this area changes. Remember mass, so let's change this. Okay, let's take this region over here. You'll see the area has decreased, and then for this region between those two arrows, the area is sort of staying constant. I'm talking about this distance between the airfoil and the upper streamline. And farther downstream on the airfoil, the area has increased again. So if I have the same mass flow rate going through my, so these are the four areas, A1, A2, and A3, and the areas A2 is smaller than A3 and smaller than A1. So I get a decrease in area and then an increase in area. And if you remember, the mass flow rate is rho, so mass flow rate per unit density, or divided by density, is the velocity of the flow multiplied by the area. And since I have no mass flow rate going out of this, all the mass flow rate is coming through my area A1. This is an impermeable surface, so there is no mass flow rate going to my airfoil or crossing the airfoil, and that's a streamline, so there is no mass flow rate going through the air. So that same mass flow rate is going, that's going through area 1 will go through area 2 and will go through area 3. And since the mass flow rate per density over density is, so that's it, is V velocity times area A is a constant, then what does this tell us about the velocities V1, V2, and V3? Since A2 is smaller than both those areas A1 and A3, then so let's just erase here. So what does this tell us about What does this tell us about the velocities u1, u2, and u3 since u times a is a constant? Well, it tells us that we're going to get the fastest velocity at u2. So u2 will be larger than u1 and u3. And now let's go one step further and look at Mr. Bernoulli. What did Mr. Bernoulli tell us for an inviscid flow? So we're assuming that we're viscosity, we're far away from the boundary layer where viscosity is concentrated, or we can say that the boundary layer is so thin that this area is not affected by the thickness of the boundary layer. So we can invoke Mr. Bernoulli that tells us that the P plus half rho u square is a constant. Half rho u square, so u square is a constant. That's over a streamline. So if I take this type of streamline here and I try to look at what, so it's close enough to the surface of the airfoil, but not too close to the boundary layer. So what is, if along that streamline these two quantities, the static pressure and the dynamic head, are, when you sum them up, they're constant, then they're constant here and here and here. So what is the pressure doing at section area A1, A2, and A3? Well, the pressure actually now has a relationship that goes with similar to the area. So my pressure at level 2 is actually going to be lower than the pressure at section 1 and section 3. So this is my lowest pressure, this pressure is higher, and this pressure is lower. So now let's imagine that we are a fluid particle that is going along this streamline. So I start here. I start with pressure P1, and I'm heading, my momentum is taking me towards area A2. So what is the pressure? So I have high pressure here, and I have a lower pressure, a high pressure at 1 and a lower pressure at 2. So is the pressure trying to push me or to retard me? So since I have a higher pressure at 1 and a lower pressure at 2, the pressure force is helping me, is favorable. So the pressure gradient force, the difference in pressure, is supporting my motion. So here I have a favorable pressure gradient that's pushing me. Now, if I look between, in this region where there is no variation in area, the pressure is neither helping me and neither hurting me. But if I look at P2 compared to the pressure P3, so we've seen that P2 is actually less than P3. So now I am going from a region of low pressure to a region of high pressure. So the pressure is pushing again. So as a fluid element that I'm moving along this streamline, what I will notice is that I'm noticing, as I move forward, a region of higher and higher pressure. So the pressure is actually going to start retarding me. And this has strong implications on the boundary layer. We're still talking about the boundary layer theory. These types of, whether in this region the pressure helping me, helping the flow, helping push the flow forward in the direction of the flow, or retarding the flow, trying to slow it down, that has implications. So we can break an airfoil into 3 regions: a favorable pressure region, so that is what we call a negative pressure gradient, favorable pressure gradient, because the pressure gradient is negative, it's going down, it's a downward slope, so you're going downhill, so it's easy. Here it's flat, so there's no variation in pressure, it's a 0 pressure gradient. And here you have a positive pressure gradient, so the pressure is increasing, but it's not good for the flow, it's opposing the flow. Positive doesn't mean it's good, it means it's an adverse pressure gradient. And then we have this third region, the adverse pressure gradient. So I have region 1, which is a favorable pressure gradient region. Region 2 is a zero pressure gradient, and region 3 over here is an adverse pressure gradient region. And as far as the boundary layer is concerned, that action of the pressure gradient is paramount. It's very important. And in fact, you go to any boundary layer book, since we're only doing a quick introduction in this course, we're not going to cover the details of boundary layers. But when you go to a boundary layer book, you'll see that there is a full section on favorable pressure gradient, full section, theories, a full theory about the zero pressure gradient with lots of studies. So these are three different fields of study for people who are in the field. Right. So it's for us the pressure gradient will affect the boundary layer in very important ways, and particularly it affects how the shear stress acts and how the flow acts in the boundary layer itself. So now we're going to make an assumption. So we're going to forget about favorable pressure gradient boundary layers. That theory, there's a full theory on that, and a full theory on adverse pressure gradient boundary layers. The point here is to make you aware of the presence of these theories. We're only going to focus on the ZPG, the zero pressure gradient boundary layer, where I take, as an introductory part, I take the effect of the pressure out of the equation. So I'm only going forward by momentum, and that makes life a little less complicated from including the pressure gradient effect. So from now on, we're dealing with a zero pressure gradient boundary layer. And how does this apply to an airfoil? So we're going to make the assumption that an airfoil is actually really long, much longer in comparison to its thickness. So its thickness is negligible compared to its length. So we're really assuming that this is the picture that we're dealing with. So in this case, we can sort of say that the variation of the thickness, just like in the previous example that we had here, we had A1, A2, and A3. If I have a really long, really slender, that is, the thickness to length is very small, or the length to thickness is very large, then the variation between a streamline far away and the surface of the object, the variation in area is very small, so the variation in velocity will be small, and then the variation of pressure is actually going to be small. So for all practice, so this would be our first stab at the boundary layer theory. Is let's deal with airfoils as flat plates. So that's what we're saying over here. We're not dealing with airfoils as circles or bluff bodies like circular cylinders or sphere. We're dealing them with we're treating them really as lines, and that is flat lines. So they don't have an angle of attack. So the flow is coming parallel to my flow. You can imagine if I have my flow coming at an angle, that one part of the flow is going to be will have an adverse pressure gradient, and on the other part it's going to be favorable. But we're not. We're only going to focus on this guy over here, zero pressure gradient boundary layers. Okay, so now that we have said this, let's take the most interesting example. So the boundary layer has shear stress in it, and now what we're moving is that we will use the boundary layer theory to help us predict. So now that we have taken the pressure gradient term out of our system, we were only left with shear stress, and we're going to use our boundary layer theory. We're going to introduce it to help us predict what the shear stress is going to be on our flying object. So let's take this airplane. Let's cut off the rudder, the elevator, and the wings. So what you're left with is just the fuselage, which let's assume is just a cylinder, and a cylinder of constant diameter. So we're losing this, losing the wing, and losing the rudder. So we're left with a cylinder. So this is the cylinder that we're left with. So the cylinder is of diameter d, which is the diameter of the fuselage, and the length is just the length of the airplane. This is L. And what we're saying is that this is a constant diameter cylinder. Now let's take a pair of scissors and cut the cylinder open. So more like if you have a toilet paper roll, you just take a pair of scissors and cut longitudinally from one end to the other, and then you split it apart, so you open it up. So you take those, so now it's cut, so you open it up and roll it out, so that circle is going to become a line. That diameter is d, so the circumference is pi d. So when I roll it out, I'm going to get an airfoil of that cylinder. When I roll it out, I cut along with a scissor, I open it up, I get a flat plate or a sheet of paper or a sheet of cardboard that is pi d in width and still the same length as the original cylinder that I started with. Alright, so now this is getting to look more and more like a flat plate. So I have my free stream velocity coming over the top surface of the airplane. So here is the top surface of my airplane, the fuselage in particular. It has an area, the surface area is the pi d, which is the width, times the length L. Okay, so here's a justification sort of, or practical application why we can start with flat plate boundary layers. So then if I look at this flat plate, let's now define our coordinate system. So from a top view, this was your this was the fuselage that we developed and rolled out into a sheet or a plate. So our coordinate system is x. It's measured it measures the distance from the leading edge. The incoming flow is u infinity. And if I look at a side view now, the side view to this plate, I'm going to only see the length L of the plate and the thickness of the plate. So still I use the same coordinate system x, and I will notice that there is a growth of boundary layer, just like we have seen before, and that boundary layer has a variation of velocity as we see over here. And what you will notice is that for a certain distance x critical from the leading edge of my flat plate, I expect to have a laminar boundary layer, and beyond a critical x critical from the leading edge, beyond that point I expect to get a turbulent boundary layer. And within the, so when we say that this is a viscous boundary layer, we're saying that the shear, the strain rate and the shear stress are the strain rate in particular, the du, this u, by dy. So now we're defining our coordinate system y, and it's measured from the plate, from the surface of the plate perpendicular to x. So that's in a side view. On a top view, the y will actually be coming out of the page towards us. So that is our y, and the variation of this velocity with y is my strain rate, and when you multiply it by viscosity, that gives you a shear stress, as we have seen before. That gives you a tau. So when I say that the boundary layer is a region of concentrated viscosity, that means this shear rate term is non-zero. And once we're outside this imaginary, or this, it's not actually imaginary, it's something you can measure but we can't see, but you can at least now imagine that it's there. Outside this region, the level of strain rate du dy is going to be very small, that this number is 0. So when you multiply 0 by viscosity, so it really annuls the effect of viscosity. That's why we say it's inviscid region. Still, the air has its viscosity, but the effect of viscosity just doesn't show up just because there is no strain rate. So that's what we mean by inviscid region and viscous region. Inside the boundary layer, we have, it's a viscous region. Outside the boundary layer, it's inviscid. The viscosity does not is not acting in there. It's just sleepy. It's dormant. So this is nomenclature, and here we're the thickness of the boundary layer delta, which is measured from the surface of the plate, is very, very small. It's very, very tiny. As we said, it's measured in millimeters, while the length of the plate is measured in meters and tens of meters. Right, so I think we'll move on to the next slide. So how this is going to help us predict the shear stress, because the boundary layer theory, what it's going to help us do, it's going to help us predict what the shear stress distribution is going to be over the surface of an airfoil. So you see here, we started with an airfoil. We then made the assumption that this airfoil is the thickness of it is much, much smaller than its length, which means that the pressure gradient is so small that we can assume that it is a flat plate. Then we jumped into a flat plate, which is where we are right now. And now this boundary layer theory is going to help us find this shear stress. Okay, so here we have just a summary of what we had before. How do you define the boundary layer thickness, delta? Delta is the boundary layer thickness. I mean, there are different definitions. There's the delta 90, delta 99. There is the momentum thickness. There is so different regions. But the more common one and the more known one is the delta 99. It tells you, if you're looking at the velocity gradient, if this is u infinity, far away from the plate, then the velocity at the boundary layer is 99. This is 0.99 u. So that's called the delta 99. 0.99, 99% of the u infinity. So we're pretty much almost the same as u infinity. U infinity. That is my u infinity. So that is called the delta 99. And people, as I said, have different definitions. They can use the delta 90. So just stick with what you have. we're sticking with delta 99 for this introductory lecture. And then now let's talk about the flow becoming laminar and turbulent. So let's go back to and step back to our definition of Reynolds number. Reynolds number is a dimensionless quantity that signifies the ratio of the inertial effect to the viscous effect. So inertial effect, so inertia over viscosity, and that's inside the fluid, inertia to viscosity. So the inertia is signified by the u infinity and the x, the size of the object and the speed at which it's flying, and the viscosity is signified by the viscosity. So for a very fast flow and very low viscosity, the effect of inertia is much important than viscosity. So let's see what this means. Now let's look at the region close to the leading edge of the flat plate, and close to the leading edge of the flat plate we have a very small the flat plate is the boundary layer is only starting to grow, and if I do just scaling of I have a velocity u infinity far away from the flat plate, which is at the boundary layer, it's u infinity, and at the flat plate I have a velocity of 0 due to no slip. But if my thickness delta is small, close to the leading edge, it's small and it's closer to 0, what does that tell me about my strain rate du dy and about my shear stress? Because delta is close to 0, that means that very close to the leading edge, my strain, so the u is u, my strain rate is so this is why you replace it with delta, which is close to 0. So my shear stress and strain rate close to the leading edge approach infinity. But then this infinite effect of viscosity, so you see, that's why we define the Reynolds number for a boundary layer based on the distance x from the leading edge, because at the leading edge we have the effect of viscosity so large, so our Reynolds number is very small, x is close to 0, and the effect of tau is going to infinity. So du dy goes to infinity. And same thing, the shear stress tau goes to infinity. So that's the story. But then as you move further and further with x, this effect starts diffusing into the outer flow. So my boundary layer thickness starts growing, and the effect of viscosity actually, again, the effect of viscosity scales with the strain rate, which is du dy. The u scales with the u infinity, and the y scales with the boundary layer thickness. And as my boundary layer thickness starts growing, the du dy gets smaller and smaller as I move further and further in x. So you get the idea, you get the point why it makes sense to define the Reynolds number for a flat plate to be based on x. And as you move further and further, the effect of viscosity diffuses even becomes weaker and weaker, and it loses its effect to inertia, and now inertia takes over and the flow becomes turbulent in this region and onward from the critical. So this is the primarily the story that we would like to at least vouch for in a boundary layer theory. This is a simplistic view of it, but it's a realistic one. And now we said that my shear stress, to get my shear stress mu du dy, I need to get the strain rate, and we said that the strain rate scales with u infinity divided by the y, which is my delta. So I'd better know what my growth rate delta of my boundary layer with x is. So before I get my shear stress, I need to get my growth rate of delta with x, and many people have worked on this before, and they have already put this in papers, and people have taken them in books. So we're going to take this result at face value. So I can predict the boundary layer thickness delta at any location inside within the boundary layer if I know what my Reynolds number is. So if my RE based on X is less than 1,000,000, I expect my flow to be laminar, and I expect my boundary layer thickness to go with Reynolds number to the 1/2 to the square root. But if my flow turns to become turbulent, the growth relationship of the boundary layer becomes turbulent. That's a turbulent flow happens when Reynolds number based on X goes beyond 1,000,000, and I get a 1/7 low growth relationship of the boundary layer. So now you guessed it right. If now I take my velocity divided by delta, I'm going to expect that my shear stress tau is going to scale with u over delta. So let's look at the shear stress, and here the shear stress tau, we're reporting it as a skin friction coefficient. This is a local coefficient, so when I have Rex, that means it's the local Reynolds number at a location X from the leading edge. Or eventually, there is the Reynolds number based on the plate itself. So the whole plate has a length L from the leading edge. Then you'll see that this is going to be REL. So it's the Reynolds number of the full length plate. And same thing with the wall shear stress. I can get the wall shear stress at any location X, but as we said, we report it as a skin friction coefficient. And same story, it scales with Reynolds number to the 1/2 for a laminar boundary layer. So same limits on the Reynolds number, less than 1,000,000, above 1,000,000, and it has a 1/7 power law for a turbulent boundary layer. So that's my local skin friction. So now I have found the shear stress, and we normalize the wall shear stress to get the skin friction by the dynamic head, 1/2 rho u infinity square, and the u infinity is it's the incoming flow velocity, and this actually should be rho infinity, so it's the fluid density far away from the flat plate. So it doesn't have doesn't include the effect of the flat plate. If there's an increase in temperature or compressibility or anything, we're dealing with incompressible flows. But just to say, it's a convention to stick rho infinity. That means it's far away. So now I found the local shear stress here. I found this gives me I can predict what the local shear stress at each and every point. And now if I have, remember, we were a flat plate, we were the fuselage of an airplane, then we went into a flat plate, and then we went into a cylinder, and then we went into a flat plate. So this flat plate really is the fuselage, and if I want now to know what the total shear stress force over the whole fuselage of the airplane, then I need to sum up locally what each one of those shear stress multiplied by its area for the whole length of the plate, and that's what we do next. So we're by summing, we mean to integrate. So my F friction, or F due to shear stress, F tau, from the leading edge of the plate to the trailing edge of the plate is going to be the integral of tau times dA. and just integrate over the whole length of the plate. So this is my tau. Stick it in here, and what is the dA? It is this dx multiplied by the width into the page, which is b. Remember the pi d of the fuselage of the cylinder. So you stick the tau wall here, you stick the dA, which is dx times b, right over here. So Reynolds number has x in it, so you get a relationship with x. So that would be the, and you integrate over the whole area of the plate from x equals 0 to x equal L. And you get the total friction force on this flat plate, which we will call just drag, and the F drag. And this F drag, it's reported here in terms of the drag coefficient. So we've already included the effect of the B times L. We divide by BL, and the dynamic head half rho U infinity squared. And we, as we expect, we're going to get the same relationship, a 1/2 power low a square root power a square root dependency for the laminar case, for the laminar part of my plate. If I had a laminar plate. So here it's based on L, as you can see. So we're taking the whole. So what we do here is we compute Reynolds number based on L. If my Reynolds number based on L is less than 1,000,000, then I'm just going to, then the entirety of the flow over the plate is laminar, and the drag force, the dimensionless drag force, or which is the drag coefficient, is going to be this number. And if my Reynolds number based on L is larger than 1,000,000, I'd expect that part of my flow is going to be laminar, part of my flow is going to be turbulent. And this includes both effects. So this is the total force on my plate from the leading edge to the trailing edge. So keep that in mind. Okay, so here we want to do a problem on to actually we started by saying we want to predict the viscous friction forces over the airplane's fuselage. We can do the same story for the wings and for the rudder and the elevator elements or wings, but that's you know, we can still do it. It's just going to take more time, but you can still do it yourself at home. Okay, so let's see. The first thing, so they ask us to compute the viscous friction force. So the